Yes, hi everybody. A great evening from my side. Yes, welcome to another NEET Byte session. So, yes, today we are going to discuss about kinetic theory of gases. And I'm seeing some names on the chat here. Hi Prasan, hello Samresh, hi Kushika. Good evening to all of you. So guys, if we yes, hi Aditi, hi Mrudang, hello Gurpreet. Good evening to all of you. So yes, so guys, as we see the statistics means the last year statistics, so we'll come to know that at least one question will be coming. Okay, sometimes it happens that there is no question, you won't find any question in the exam from this chapter, but yes, sometimes at least one question sometimes come. So we have various important topics in this. Okay, so we'll just discuss a few, I'll just give the summary in a brief, and then we'll be just taking up the questions. Okay, so yes, so kinetic theory of gases. And one more thing I would just like to tell you here, that this part is already in the chemistry as well, so probably the student find a bit easier. So all the gas laws and everything will be there. Okay, so I'll just give a brief idea what all things are important in this. Okay, so first we'll talk about the pressure exerted on the wall. Okay, so here I'm just going to draw. Suppose I have a cube here. Okay, and this is the entire gas is being enclosed. Okay, so what this gas is doing, this gas is putting some pressure onto the walls, right? So that pressure is coming out to be 1 upon 3 rho v square. So here v, just a moment, 1 upon 3 rho v square, and here v is nothing but v rms. This is root mean square speed. Okay, this is root mean square speed, and this the main, like if you just wanted to see the physical meaning of it, so this is nothing but v rms is nothing, it's like under root of, if you take the individual molecules and you just take the square of their speeds, and you're just taking the average of all the molecules here, so this is nothing but the vrms. Similarly, we do have we do have average velocity as well. So vrms, we do have a formula, that is under root 3 rt upon m. And here, if I'm talking, whenever I'm writing the formula in the terms of the gas constant, it means I'm writing it for 1 mole. If you're writing the same formula in the terms of single molecule, so what you can do is, this is 3 kt upon m. K is here is Boltzmann constant. Okay, anyway, so let's just go ahead, and here we average, if you want to calculate, that is sum of all the velocities, right? And you just need to take the sum and you just divide with the total number of the molecules present. Okay, so these are the important things, means the pressure and rest of the gas laws, guys. You know that we do have Boyle's law, then we do have Charles law, Gay-Lussac law, okay, Dalton law of partial pressure, right? Partial pressure. Okay, and we do have Avogadro's law. Just a moment. Okay, these are the following law, like you must have studied in the chemistry as well. So these are the important one. On the basis of these one, you might find a question, or we do have the ideal gas equation, that is PV equals to nRT. Okay, so I mean, these are the basic things that you need to study. Okay, and you definitely be finding a lot of questions on the basis of these topics that I have discussed. So let's just take a few numericals, guys. Okay, so I do have a numerical here. Two vessels separately contain two ideal gases, A and B, at the same temperature. So the pressure of the A being twice that of B under such conditions, the density of A is found to be 1.5 times the density of the B, the ratio of the molecular weight you need to calculate. So guys, before taking up the question, I would like to tell you the relation between the density and the pressure and the volume as well. Okay, so here, this is the ideal gas equation, PV equals to nRT, right? This is PV equals to nRT. Just a moment. Fine. So what you can do is, here, if you want to calculate the density, so how can you write this number of moles? This is molecular, this is the total mass of the gas, divide the molecular mass, right? So here you can calculate that if you are bringing this V here at the bottom, so this will become the density. So this will be in this way. Am I right? Right? So this is the density relation with the other terms like the pressure and the molecular weight as well. So here you can see in the questions, it is being given here that the two ideal gases A and B, and they are at the same temperature. Okay, and the pressure of A means, if you are writing the pressure of A is equals to twice the pressure of B, I can write it in this way, or basically you can write it in this way, right? And the densities relations is also given. Okay, so I can write it in this way as well, that the density of A is found to be 1.5 times the density of B. Okay, so this is density of A is almost 1.5, just a moment, 1.5 times of the density of B, right? So let's just put it in the formula. That's all we need to do it. So yeah, so here what I'm going to do, that density, this is rho, okay, is equals to Pm upon RT. Okay, this is for A, so I can write for A here and A here as well, and similarly I can do it for B as well. So this is P of B, molecular weight of B, and you know that the temperature is constant, means the temperature is same in both the cases. So R is automatically a gas constant, that has to be constant. So we can divide these two. So this is rho A and this is rho B. So this going to come as PA MA, right? And this is PB MB. Is that right? And this ratio is already given to you as 1.5, right? If this is 1.5, you can write it in this way as 3 by 2. And what is PA upon PB? Okay, PA upon PB is 2 again. So this part, I'm going to take it up with a different color, guys. This part is given to you as 2. So what is MA upon MB? MA upon MB is 3 upon 2 divide 1 upon 2 is going to come as 3 by 4, right? So this is the ratio. And guys, there is no, I don't find very difficult, I don't find this one very difficult, right? So this going to be the answer, the first one, the A part has to be the correct one, right? So you just need to remember. And one more thing, guys, how much time does it take to derive this one? Not that much time. So you should not remember so many formulas whenever you are preparing for the competition. So the only thing that you need to remember is the ideal gas equation. It would hardly take 2 seconds to derive this one, and rest is you just need to put the values. Okay. Yes, Dishant, it is the kinetic theory of gases. Exactly. Yes. So let's just move to another question. This one is the VT diagram. Okay, what is the relation between the P1 and P2? Here the graph is being shown, and we do have two graphs, or you can take the two gases. One gas is following this one, and the another one is following this one. So you can consider the pressure for the first gas is coming out to be P1, and the second one it is coming out to be P2. And guys, these are the thetas, means the angle is being made with the temperature axis. So can anybody tell me what would be the slope represent here? What would be the slope represent here? Yes. Okay, I'm not seeing any answers on the chat box anyway. So guys, you know that this is the ideal gas equation, PV equals to nRT, right? If I wanted to, what does slope represent? That is slope of this curve representing V by T, right? So I need to just create V by T here. So that is NR upon P. So means the slope is inversely proportional to the pressure according to this equation. So which graph has the more slope? You can see the P2 has more slope as compared to P1, and it is lesser than, means this slope is inversely proportional to the pressure. So whichever has less slope would be having the high value of the pressure. Okay, so here the P1 has to be greater than P2 because the slope of P1 is less than slope of P2. Okay, so we can choose the option this one. Okay, fine guys, do you have any doubts? If you guys have it, just put it on the chat box. Okay, so let's just move ahead guys. Yes, we do have another question here, where at 10 degrees Celsius, the value of the density of a fixed mass of the ideal gas. We do have an ideal gas where we are keeping it at 10 degrees Celsius, and the ratio of the density divided by the pressure is X. Okay, so what is the density upon pressure? That I have already told you that the density, we have just derived it in the first slide, that is Pm upon RT, right? So this is Pm upon RT, where you can just create the ratio that is being given in the question, and that is nothing but M upon RT. Okay, and this is being given as X. Okay, so this at 10 degrees Celsius, you can see that the ideal gas is keeping at this temperature, sorry, at this temperature, yes. So the ratio of the density upon the pressure is coming out to be X, right? So guys, can I just tell this one that M upon R, anyway, this is the molecular weight, right? This is the molecular weight of the gas, and this is the R is the gas constant. So can I write that X into T has to be constant for the same gas, because we are going to change the temperature after some time, and we need to calculate the same ratio for different temperature. So what I'm going to do is, I just came to know that the product of X and T has to be constant. So what I can do is, I can just use this equation. X into T has to be constant, right? So X and T at temperature 10 degrees Celsius has to be equals to X into T at what temperature? 110 degrees Celsius. Okay, so you know that you have to convert it into Kelvin, because that is the standard form of the temperature. So what you have to do is, temperature, this is given as 10, so it will become as 273 plus 10, that would become as 283, right? And similarly, for this one, we need to calculate this ratio X dash. That's what they are asking, right? And this one, 110, how it would be? That would become 273 plus 110, that is coming out to be 383, right? So this is 383. So now X dash is coming out to be 283 upon 383x. So this is the new ratio that is being derived from the equation. Okay, so this option has to be the correct one, the last one, the D option. We need to mark it. This is the correct one. Is that understood with everybody here? Okay, so now I have few questions more. Yeah, I mean, this question was asked in 1996. This was like pretty old question. So here, at 0 Kelvin, which of the following properties of the gas will be zero? Yes, according to you, if we just drop the temperature to 0 degrees Celsius, according to you, which of the following quantity will be zero? So guys, I have just told you that I have just told you that the vrms means the root mean square speed is nothing but under root 3 rt upon m, right? And vrms is directly proportional to, you can say, the under root of the temperature. And guys, the kinetic energy of a gas, whenever the gas molecules are vibrating to each other, right? They are colliding whenever you give the temperature. So what is happening in that case, that the kinetic energy is associated with any gas is just because of the temperature. If you are rising the temperature, the molecules will more vibrating. They will start more, rigorously they will be vibrating. Okay, and kinetic energy is just because of the temperature. You can see the if you are heating up a gas, so that gas will be having more kinetic energy. So if you are dropping down, if you are dropping down the temperature of a gas is almost 0 degrees Celsius, so the vrms coming out to be almost zero. Okay, so kinetic energy, because kinetic energy is what, half mv square, right? So the v, if you can see, the v is coming out to be zero, so kinetic energy definitely has to be zero. And rest of the quantities, if you are looking at that, potential energy is just because of the intermolecular forces of the attraction, intermolecular attraction forces, right? Density, again, is dependent on all these factors, not this one, because if you're writing density as pm upon rt, so if you're keeping the temperature zero, it has to be infinite. Okay, and the mass never goes out, because mass is something that will remain constant until you're moving with the speed of the light, right? That is Einstein, all that relativity theory. So all, from looking all the options, this one is the correct one, guys. The kinetic energy of the gas will become zero. Okay, so yes, the relation between the p and the e means the pressure and the energy. Okay, so what you can do is here, this is guys, the energy p is 1 by 3 rho v square, and p you can write it in this way, 1 by 3, this is rho. This is, what is rho? Rho is nothing, mass upon volume, right? This is v square. This v and this v is different. Okay, so you can write here as pv is equals to 1 upon 3 mv square. Okay, and probably here, kinetic energy. What is kinetic energy? Kinetic energy is nothing but half m v square. Okay. If we just divide these two equations, so what are you getting here? PV upon KE is equals to 2 upon 3. So P V is coming out to be 2 by 3 of KE. So this is the relation between the energy part and the pressure. So here they have eliminated the volume part here. So this one has to be the correct one, the A part. These are the old questions that was asked in 1991. So guys, this is how you have to do it. I guess it's understandable to everybody. Okay, let's just move ahead. This one, this is gonna be the last one, I guess. Then we'll wind it up. So there are two containers, guys. A and B are partially filled with the water. Okay, they are partially filled. So I'm just going to make this one. Okay, these are, this is A, this is B, and they are partially filled with the water. So and they are closed as well. It means they are not open to the atmosphere. So here the volume of the A is twice that the volume of the B. So if you are keeping the volume, and it contains half the amount of the water in the B. So what is happening here? The amount of the water in the A is twice the amount, twice in the, as compared to the B. Okay, the amount of the water, and we are keeping at both the containers at the same temperature. So you need to come up with the whether we are keeping at the same temperature, and the water vapor in the containers will have pressure, means it will be having some water vapors above the liquid, it will be having as well. So here I'm considering this one as a pressure A, and here I'm considering this one as pressure B. So according to you, how this ratio will be, whether it's 1 by 2, 1 by 1, 2 ratio 1, 4 ratio 1, according to you, what do you think? Yes. Okay, guys, actually, how the vapor is being created, how the vapor are being created, because it is coming from the surface, and we are keeping them in this container. And as the temperature is same to both of the liquid, the vapor pressure coming out to be same. Vapor pressure here and the vapor pressure being created here, that has to be same. It just depend on the temperature. Because, and one more thing, the surface as well, because as you can see, the surfaces are equal, because vapors are being generated from the surface. They are not just doing it from the bulk of the liquid. They are not coming from the bottom of the liquid, they are coming from the surface. So as surface is same and the temperature is same, the vapor pressure has to be equal to both of the gases. I just took this question because most of the people generally think that more the liquid, more will be the pressure. It is not like that. It doesn't work like that. Okay, so you have to think in this way. So that's all, guys. Yes. So these are the questions that we have discussed today. We have discussed a lot of questions actually. So actually, I'll just wind it up by saying one sentence, guys. The questions coming from these chapters are not that much difficult. The only thing that you need to understand, you just need to drive small formulas, and you just need to put up the values there. This is how you have to do it. And we cannot neglect this chapter. This is one of the important chapters as well. So guys, that's all. And you guys can just browse these links to get to know to more information about the Meritnation. And thank you so much, guys, for attending this lecture, and we will be meeting up in the next one, okay, with a new topic. Thank you so much, guys. Bye bye, take care.